We also have neutron that we need to be aware of. Notice, what is that? What's happening with neutron radiation, guys? What is it? It's just a neutron. All right, so you're losing a neutron there. Its symbol is going to be just an N. Okay, and then proton. Same thing. We've talked about those. So those are some symbols that we can see. We're familiar with them. It's not types of radiation per se, but it's symbols that could be things that could be given off in a nuclear reaction. Big thing, guys, that you want to make sure that you are aware of, okay, is that, conservation of matter, okay, and charge. All right, so that's the name of the game with these equations that we're going to be writing. You guys are going to be practicing probably tomorrow. Okay. So now those are the symbols. Let's kind of go through and start talking about each type of decay and what's actually happening. Okay, what's causing it. Questions? Can I go on? All right, so the first thing, guys, we got to learn about is the separation of nuclear particles by electric or magnetic fields. This should be pretty obvious to us, right? In a magnetic field, guys, we've got a positive and a negative component. Okay, so if you think about the particles, if you're taking a look at table O that we just went over, all right, what particles are negatively charged? Well, those are going to be your beta rays. So they would typically go and be separated out. They're going to be attracted toward the positive magnetic field, where alpha rays are going to be attracted to the negative component of the magnetic field. And then gamma rays, they're neutral, so they would just be shot straight through. So you can kind of get them to separate just by introducing a magnetic field. All right, it should be pretty obvious to us. That shouldn't be anything crazy, but you have that graphic to look at that can help you kind of understand it visually, give you a visual for it. So radioactive decay, guys, the following decays occur in nature as a result of unstable neutron to proton ratios. What is the key? What's that mass that we're looking for where they will start to naturally occur? 83. Greater than 83, that's where we typically will have that natural stuff where they're unstable. Okay. All right, so our first mode of decay, guys, it's the most common one, alpha decay. It's a transmission where an unstable nucleus emits alpha particles. They are products in the reaction. Okay, alpha particles are products in the reaction, and the nucleus becomes smaller. Okay, becomes smaller with a less positive charge. Alpha emission is characteristic of heavy nuclei. Again, especially those ones greater than 83. And I give you an example there where we have plutonium-240. It's breaking down into uranium-236, and then an alpha particle. Notice, guys, what an alpha particle is. It's the nucleus of a helium atom. Okay, it's the nucleus of a helium atom. It's not the electrons. Remember, with nuclear chemistry, it has nothing to do with the electrons. Okay, so alpha particle is the is the nucleus of a helium atom. Now, what's the purpose of decay, guys? What are elements trying to do? Become stable. So they're going to keep decaying until they reach an isotope that is stable. All right, so that could be, one decay, it could be another decay, it could be, several series, but they're going to keep decaying until it becomes stable. That's the whole purpose of this. All right, now, how long that takes, well, that's dependent upon half-life and things like that, which we'll get into more and more this week. So what we're, again, harnessing in those nuclear power plants is the energy that's being released in those decay modes. All right, so alpha decay is the first one. It can be summarized as follows, guys. Atomic number is going to decrease by 2. The number of protons then will also decrease by 2. Mass is going to decrease by 4. And the number of neutrons decreases by 2. All right, again, that's just simple math that we're looking at when we balance those things out. Notice right here, this is what I was talking about, how long it takes for the decay of plutonium-239 down to uranium-235. It takes about 24,000 years. So it doesn't just happen instantaneously. Okay? And while it's happening, it's giving off that energy, and that's what we're trying to harness there in nuclear power plants. Okay? So we can use it. Obviously, there's pros and cons to that. But that's kind of a brief, very, very brief summary of what's taking place there. All right. So here we go. This is the type of problem that you're going to see on your test. We got to make sure that the charge and mass is conserved on both sides. So with alpha decay, we have what we call the parent. That's terrible handwriting. Why can't I? Parent nuclide. Okay, it's called the parent nuclide, and it breaks down or decays into your particle that you're giving off, which in this case is an alpha particle, and what's called the daughter nuclide. Okay, those are two terms that you could see. So we got to figure it out. Knowing that it's alpha decay, here's our alpha particle. All right, we know that that's being released. We got to figure out what the daughter nuclide is going to be. So do the math. What's 220 minus 4? That's our new mass. And then 87 minus 2 is, what element's 85? AT. Okay? Now, number 2, they don't give us the particle, but they tell us up here it's alpha decay, so you've got to know that one of those pieces that are going to be left over is going to be an alpha particle. So I would fill that in. All right, that's not going to change. You can look that up in your reference packet. Now we got to figure out our daughter nuclide, which does it matter which one comes first or which one comes second? No. Okay. What's our mass going to be, our new mass? 218. 222 minus 4. And then our new atomic number or number of protons is going to be, which is what element? PO, polonium. Bolognium? That'd be a good tasting element, right? Second mode of decay, guys. This is the next most common, beta decay. So this is where a nucleus emits a beta particle. Guys, a beta particle is just an electron. Okay, it's just an electron. Do electrons have mass? Absolutely not. Okay. As a result of nuclear disintegration, so this is where something is said to undergo beta decay. It's called a beta emitter. Okay, so it gives off that beta particle. You can summarize this as the following, guys. The atomic number is going to increase by 1. Protons, which means the protons increases by 1, but the mass stays the same. All right, the mass is going to stay the same. And then the neutrons, guys, your number of neutrons is going to decrease by 1 because your protons goes up, which takes the place of the mass of that neutron. So it's still giving off a neutron, but the mass stays the same. That's the piece that's kind of crazy. But just look at what it is. Follow the math. If we were to add up the right side, 56 plus a negative 1, well, that's 55. So cesium-137 emitted a beta particle. Mass stayed the same, but the number of protons increased by 1, meaning that the neutrons decreased by 1. Okay? So, same idea. This is not difficult math, guys. It's understanding when it says which particle is decaying, you got to know where to look, and that's table O. Then you're just going to balance it out. I want you guys to go through and do these 3, and then we'll go over them together. Okay? So, when you are asked to show or to write the nuclear equation for beta decay or alpha decay, guys, it's not going to give you it. You're going to have to fill it in, know where to look. Again, table O. So what I would do is write whatever mode of decay first. You're not going to obviously be given boxes, but you'll have a line. We'll do that first. It's just easier to look at the math. I know that my mass will stay the same here. 6. Now, it's a negative 1 plus that, right? Minus it. So what's it going to be over here? 7, because this whole right side is going to add up to 6. And then what element is that going to be? Nitrogen. Down here, still 214. All right, my atomic number is going to be 83. And what element is that? Bismuth. Okay, guys, this is not that complicated. It's keeping track of your modes of decay. That's the hardest part about it, is knowing, again, where to look. Positron emission. Okay, this occurs when a positron is produced during the conversion of a proton to a neutron. Okay, so this is basically where a proton becomes that neutron, and it gives off basically what looks like a positive electron. Okay, but it's not necessarily the same thing, okay, but it has that type of effect. So your neutron, so it basically just loses the charge. That's all you're doing here, guys, is that it's changing the charge. Mass doesn't change because a proton becomes that neutron. It's just emitting that positive charge. All right, so the atomic number decreases by 1. Number of protons then will decrease by 1. Mass will again stay the same. So this is the opposite of beta emission. Okay, positron emission is the opposite of beta in terms of charge. Mass stays the same, but the charge is the only thing that changes. So beta is negative, positron is positive. It should be easy, hopefully, to keep track of those. You guys go ahead and do these examples. We'll go over them in just a second. All right, there's argon. So they add up. Remember, the right side is going to equal the left side. So here we go. Positron emission. So right there. All right, so that's going to be that positron piece. Masses will stay the same. So 81, 19. What's my mass going to, or my atomic number going to be for number 2? 36, which is what element? Krypton. And then down here it's going to be, which is fluorine. It's that simple, guys. Don't make it harder than it needs to be. Last thing, gamma rays. They are a highly penetrating type of radiation, similar to X-rays and light. So it's all energy is what it is, which is why we see that photon symbol here in our diagram. So nothing about the nucleus, guys, changes. It's just energy, which again is why these are so dangerous, is because it's energy, which makes them the most destructive form of that nuclear radiation. All right. So there's no math involved here. If you see a gamma problem, which I think is a lot less likely than alpha or beta or even positron, nothing changes, guys. Everything stays the same. You just have that 0 over 0 and the y for gamma. All right. Any questions?